gauge theory. So, Joseph, please.
Right. Yeah, so I'm going to talk to you about gauge theories. That's a very broad topic, as you can tell. But I'll tell you more specifically in a second what I'm going to talk about. Let me start with a disclaimer. So there's two parts of this disclaimer. The first is that I'm dyslexic, so there are going to be some words in this talk that I'm going to mispronounce. And sometimes I say the wrong word when I mean something else. If that happens and you don't understand me, just feel free to ask. I'm happy. I also realize I sometimes speak a bit quick. Just ask. And the second thing is, I like to try and do talks in a slightly different way to what is normal or what is traditional. This might not work, so I'm going to try and tell a story throughout this talk. If it doesn't work, I again apologize for that. So, given this is a workshop, let me tell you what I actually work on. So my main... Oh yeah. So the main focus of my work is on symmetries. And this really falls into one of two categories. So I either do classification theorems, classifying different gauge symmetries or classifying global symmetries, and then from that go into more model building type activities. The other side of my work is more formal. It's looking at topological field theories. And these we study these because they don't have much of the faff that goes on with traditional theories like there's no path integral, there's no Lagrangian, they're very simple. And you can really get to the heart of what it means to be a symmetry, what it means to have things like Toft anomalies and things like that. The downside of this is that you need fairly rigorous mathematics, in this case category theory or higher category theory. So it can be sometimes quite complicated to talk about a topic like this. So I'm going to focus on this side of it, and really this talk is going to be split into two halves. So the first half, we're going to look at the classification and general theorems related to classification, and then the second half, we will look at more model building exercises. So this is going to be the layout of the talk. I'm going to be looking at, in the first half, the guts of SU48. I'm using the guts very loosely here. I'm not actually going to talk about unification. It's just easier to say guts than it is to say semi-simple extension of the standard model. And in the second half of the talk, I'm going to take one specific example of one of these guts, the example of SU4 plus SP6 plus SP6, and we're going to look at that in more detail. We're going to do basically model building, and we're going to try and explain the fermion masses. So in the middle, we'll take a small brain break, as I like to call it. Research suggests that the pivot time for talk is about 18 minutes long, which is why TED Talks are 18 minutes long. So these two halves will be roughly around that time. I'm also going to focus on the broader picture rather than the nitty-gritty details of what's going on. The first half is with Ben Amlach and Ben Kapayas, which was published last year, and the second half is with Joe Defeaty, who's a postdoc in Zurich. So I'm going to tell you a story. I'm going to tell you the story of where this code came about. I obviously don't need you to understand what this code is doing. There's over 3,000 lines of it. It's also really badly written. But I'm going to tell you in this first half the origin of this code, and specifically what it does. This code started in this building here. This is the Cavendish Laboratory at the University of Cambridge. Not only is it ugly, it's also pretty deadly. It's full of asbestos. So, this is where I did my PhD. And every Wednesday morning, we had this meeting called the Susie Working Group meeting, where we would sit at a table and we would discuss the things that we had been working on that week. They ended up changing the name from the Susie Working Group to the Pheno Working Group because no one actually talked about Susie in these meetings. It was a particularly rainy Wednesday morning in 2018. I know it was rainy because it was England. When, near the start of my PhD, when we had this meeting, there were 3 people in that meeting of importance. There was Joe Defeaty, Scott Malfoy, and Ben Amlach, and they were asking themselves this question. For the standard model, plus up to 3 right-handed neutrinos, what are the anomaly free sets of charge assignments under an additional U1 extension? So let's break this down to see what they were asking. They took the standard model, which is this thing. Let's ignore the Higgs sector or any scalars for now. This is really the standard model of the fermionic sector. So I've got the SU3 plus SU2 plus U1 gauge algebra, and I've got the fermionic representations. I've done 2 things. I've made everything left-handed, and I've normalize my hypercharges to 1. To integer numbers. So what Ben, Scott, and Joe were talking about in this meeting is what happens when you add an extra U1 to this variable. So if you add an extra U1, all of your fermions gain additional charges under this U1. I'm going to assume these charges are integers, which basically corresponds to the condition that this U1 actually comes from a U1 group, not, for example, a real line group. You can't choose these charges arbitrarily. You can't put like Q1 equals 10, Q2 equals minus 20, or whatever. They have to satisfy certain conditions. And these conditions come from the triangle diagrams you might be familiar with. In the context of U1 extensions of the standard model, these become a set of equations which have to be satisfied. So these are polynomial equations. So this one's quadratic, this one's cubic, in integer charges. These types of equations are called Diophantine equations, after the Greek mathematician Diophantus. Diophantus was really the founder of number theory, and it's in Diophantus's Arithmetica where Fermat wrote in the margin about Fermat's last theorem. Fermat's last theorem perhaps being the most famous example of the Diophantine equation. As Fermat's last theorem tells you, these equations are often pretty difficult to solve. Finding solutions to integer polynomial equations in the integers is not an easy task. So what Ben, Scott, and Joey ended up doing is they ended up finding the numerical solutions to these equations. They took a maximum charge, they said, let's consider charges up to a maximum charge of 10. And they scanned through every possible set of charges and plugged them into the equation, and then just made a big list of whether of these solutions that satisfy these anomaly-free equations. So I was listening to the discussion at the end of 2018, and as 2018 turned into 2019, another paper came out on the archive, which was by this collaboration here. I'm not going to try and pronounce their names because I know I'm going to do it wrong. So they were studying these U1 equations. So they were considering a different problem, which is not the standard model plus a U1, but a pure U1 case variable, in which you have n fermions, say, charged with charges, integer charges, xi. And what this collaboration was doing is they found an analytic solution for these equations. Around the same time, I was having conversations with Ben Almack and Ben Harris about more phenomenology projects that I could do. At the time, I was working on quantum mechanics, on topological backgrounds, and I wanted stuff which was closer to phenomenology. And it was suggested that we have a look at this solution and we try and use the same methods to tackle the standard model plus U1 case. It turned out that their solution, their analytic solution, used fairly standard techniques in number theory that could indeed be used to find the full solution, the analytic solution to the standard model plus U1 anomaly cancellation equations. So what does this mean? It means that we have a solution, a set of parameters that you plug in the parameters, and it will output a set of anomaly-free charge assignments that you can give a U1 extension of the standard model, or you can give a C prime model, let's say. And you can get every possible U1 set of anomaly-free set of U1 charge assignments in this way. So this is now a solved problem. As 2019 turned into 2019 to 2020, of course the world went into the global COVID pandemic. I moved up from Cambridge to my hometown of York. And around the same time, I was having conversations with the two Bens about other projects that I could do to kill a time or to kill a long time in the UK lockdowns. To tell you what we decided we could do as a project, I need to give you a brief lecture in the algebra theory. Some of you probably already know this, some of you may not, but let me say it anyways, just so we're all on the same page. First of all, I need you to know what a simple algebra is. The simple algebras are things like SON, SUN, and SPN. They're the standard things you may be familiar with. A larger category of algebras are the semi-simple algebras. These are things like the SU3 plus SU2 part of the standard model, or the SU4 plus SU2 plus SU2 Paty-Salin model. So, Perhaps these are familiar to most of you. Perhaps less familiar is the broader category of reductively algebras. So the most famous example is the standard model, which is SE3 plus SE2 plus U1. So these are semi-simple algebras plus additional U1 factors. And another example is the 4-3-2-1 model, which has this semi-simple part plus an additional U1 part. So the conversation I had with two bands about the sorts of projects that I could work on ended up going along the lines of, let's take an example. Let's take an example that we're all familiar with, which is the SO10 gut. And what can we say about the SO10 gut? We're only focusing on the fermions here, and really this diagram contains all the information you have about the SO10 gut and the fermionic content. So you have this SU48. So the 48 comes from the fact that there are 48 fermions in the standard model if you include 3 right-hand neutrinos. And at the bottom here you have the standard model gauge algebra. That might be better. This map gamma is the representation, the standard model representation of your fermions. It's basically that 3-2-1 thing, the 3 bar 1 minus 4 thing that I showed you a couple of slides ago. So this is the standard model representation of the fermions. And here you have the SO10 gut. This 16 plus 3 representation. It's the representations that fermions live in this SO10 gut. So it's 3 copies of the 16 representation. And this map alpha is how the standard model embeds into the SO10 gut. So me and the two Bens were looking at this diagram, and we were like, okay, let's take this diagram and let's generalize it. So let's replace SO10 with G, a generic gauge or a generic algebra, which kind of will correspond to our gut. We replace the 16 plus 3 representation with a generic representation beta, and we replace the specific alpha here with a more generic alpha. And we can ask for this diagram to commute. And we can ask, can we find all such diagrams that commute? The answer to that is obviously no. There are infinitely many such diagrams. So you have to start to put conditions and stuff. One set of conditions you could use is that you could make G correspond to the standard model plus an additional U1. And this corresponds to exactly the case we just looked at. You could also ask G to be reductive. Asking G to be reductive is also pretty tricky. There are also infinitely many such of these diagrams with G reductive. Just because there are infinitely many cases where you have an extra U1. I should say, by the way, if people have any questions, feel free to ask. So let's go one step further. Remember that my previous slide, I had the reductively algebras, and then I had the semi-simple. The algebras was one step in. So what happens if we ask for all G to be semi-simple? It turns out that this case is possible. So you can find all such diagrams where G is semi-simple. Well, okay, you have to add one extra condition, which is that the representation beta is free of local anomalies. Basically the equivalence of the triangle diagrams. You can also ask for it to be free of global anomalies, but that requires you to know the gauge group, whereas here we're only focusing on the gauge algebras, so you don't have that information. So as me and the two bands decided on this problem, to find all diagrams of this sort, which commute, which G is semi-simple, in other words, finding all semi-simple extensions of the standard model, SO10 being an example, we asked ourselves, is this going to be possible? How do we know that you can do this? Why should we waste our time trying to work this out? And it turns out that there are some old papers by Dinkin and others about subgroups of semi-simple algebras. And it's really these papers and the sorts of techniques which are in these papers that allow you to do this problem, allow you to solve this problem.
So can I ask you, essentially you're asking the question of what are all possible cuts that
Yes.
no other matter and
Yes.
exactly the standard model.
Yeah, exactly. So we're restricting the fermionic content to be the standard model plus 3 random neutrinos. And we're saying, can we find all of G which have representations of dimension 48, so they cover all of these fermions, such that this diagram can be, so in other words, such that they branch down to the standard model fermions.
So what's the rationale for sort of restricting the fermions? So for example, I know that I can go from SU5 to SU6. Yes? And in SU5 you have an antisymmetric and an antifundamental. In SU6 I would have an antisymmetric and 2 antifundamentals to make it anomaly free. So I added more matter. But at the point when I break SU6 to SU5, I can just make the extra matter, super heavy, and I got to SU5.
So the rationale is that you need a problem that can be solved. Like we were trying to solve a problem here, and we needed something that could be solved. If you added extra fermions, you'd replace this 48 with n, where n is some number, and you wouldn't have a well-defined problem that you could find a solution to, basically. So we had to restrict the number of fermions to be 48. It's purely at the level of we want a problem where we can find a solution, and you can only do that once you restrict to the number of fermions. So these papers kind of tell you how to form these diagrams. And after I had these discussions with the two Bens, I went away and I wrote a computer program, which is the computer program that I showed you at the very start of this talk. And what that computer program outputted was all of these diagrams, all of these, let's call them guts. I'm not going to give you any more detail about how that computer program works or what it does. Let me just give you the results. So, for one family, there are exactly 3 instances of these diagrams, and these are the cases you're probably familiar with, or these are probably the most famous cases. So you have the SU5 guts, the SU10 guts, and Patti Salam. And you may know that SU5 embeds into SO10, and Patti Salam also embeds into SO10. So in this sense, we would say that SO10 is maximal, because the other 2 things embed into it, and it doesn't embed into anything else. I will use that to maximal what follows. So what about the 2-family case? Here you have 45 fermions, 45 algebras. I've given some examples here. So you have SO10 with an SU2 flavor symmetry. You have things like SU4 plus SP4 plus SP4, which is some sort of Electroweak flavor unification. You have SU8 plus SU2 plus SU2, which is some sort of color flavor unification. And then you've got some weird other stuff going on. So what about the 3-family case? In the 3-family case, there are 340 of these algebras, 24 of which are maximal in the sense of the previous slide. And these are the 24 maximal ones. So there's SU4 plus SU6 plus SU6, which is what I'm going to talk about in the second half of the talk. This is really Electroweak flavor unification. You've got things like 3 copies of SO10, SO10 plus what turns out to be SO3, flavor symmetry, and a bunch of other stuff. Most of this, or nearly actually all of this, is based on SO10, SU5, and Patti Salam. So there's nothing really exciting in the sense there's no new ways to combine the gauge groups. The only things we actually do find in the end is novel ways to combine the gauge group and flavor. So really, in the end, this becomes a question of how do you combine the gauge group and flavor? So this kind of summarizes, this kind of is the result of this computer program, and really the result of, or the end of this first half of the talk. So let me summarize the 3 things I want you to take from this first half of the talk. So the first one is progress has been made in classifying guts or extensions of the standard model in a variety of different arenas, whether it be U1 extensions, whether it be semi-simple extensions, just classifying every possible way you could extend the standard model gauge group. The second thing I wanted to say is that there are 340 different possibilities of semi-simple extensions of the standard model, and as Chava said, that's with the condition that you don't add any extra fermions. Most of these have never been looked at in any detail, and some of them are quite interesting. So there's a lot of possibilities here of different models that can be studied. The most important thing for the second half of this talk is that I have not once mentioned anything about scalars. This whole first half of the talk is mentioned. I haven't talked about the Higgs or anything like that, or symmetry breaking. I've only talked about the problem of how do you get the fermions right? How do you combine the fermions in the right way into a gut?
So how many of these actually unify?
This we don't know. In terms of the gauge group, yeah, we don't know this. Because I think this not depend on the scalars.
Sorry, what was the question?
How many of these actually unify? Yes, I mean,
Okay, okay.
do the gauge couplings actually
Yeah. So the problem with questions like this is that you have to do them. If there was a way to do that systematically on each of these possibilities, then this would be an amazing question to ask, right? But I don't know any way of systematically going through this list and checking this condition. So any sort of condition that you can somehow systematically do, this becomes useful. I mean, okay.
It's because if you could just give me one, I would be already.
That unify. I mean, it's
so
not
because I don't know any other example but SC5.
yeah.
And then the rest is.
But it can be answered at the moment because there are no scalars yet.
Right. But then you have to build a complete thing.
Yeah.
And you have to stay completely non-systematic, because once you have supersymmetry, then all the scalars you might have to break symmetry, except that you would completely destroy the approach.
I will get onto that in a second, actually. Okay, so like I said, so basically I don't know. Most of them are based on SU5, SO10, with some sort of flavour symmetry, so they may unify the same way that they unify, but it's quite hard to do a systematic study of all of them. Okay, so like I said at the start of this talk, we're going to do what I like to call a brain break, where if you want to stop thinking about anything or about the talk, you can now. I'm going to just tell you something completely random, which is when me and the two bands finished this talk, we had to choose a name for it, and when you're coming up with names for papers, there's often certain criteria that you want to satisfy. What we ended up calling this paper, for a reason I actually don't really know, we ended up calling this unification, which is the longest non-technical word in the English language. And being someone who is dyslexic finds it incredibly difficult to say and spell. If you search this on Archive, as one does, you end up with 5 papers. 2 of which are co-authored by me. So this one I've been talking about, and this one that cited it. And then the other 3 are somewhat interesting. So this first one is about some machine learner stuff. I don't know why they have this word in there. But yeah, so that's some machine learner stuff where they use this word to do something. There's this paper down here, which looked at word length. And obviously this word comes in a paper about word length. And then there's this paper here, about quantum Godwin's law. So what this paper is about, so Godwin's law is basically that as the length of an internet discussion gets longer, the probability of converging on any given topic really converges to 1. And what this paper is about is how this conversion of internet discussions in the presence of a quantum internet will go from factorial speed to polynomial speed. You will notice the date of this paper. It is 1 day before April Fool's. So this is a fun read, it's not a true paper. So returning to, so the last thing I want to say about this this first half of the talk brings us back to the question we had over here, which is, what about CC? And really, what about superfunctionality in the unification? In other words, we've done the case of the standard model. What about the case of supersymmetry? What about the case of the standard model plus symmetric fermions, as Chapter was talking about? So this is something I'm working on with Max and a PhD student at Cornell. And if people have any ideas or any suggestions of sorts of fermionic sets of fermionic contents that you want to see the semi-simple extension, or that you want to see if they can be classified into guts, we'd be happy to hear about it, because we're in the process of putting together like a list of these sorts of models. Okay, so really this is the first half of the talk, and I'm now going to go into the second half of this talk, which, if you didn't understand anything I've said, you can join in here. It's kind of disconnected, it's kind of connected, but hopefully you'll follow. So what am I about to do? I'm about to pick one extension. So one extension of the list we just found. I'm then going to construct a complete UV theory with scalars and everything. So I'm going to tell you how we're going to break symmetry. And then I'm going to account for the hierarchical masses and mixes in the fermionic sector. In other words, the CKM matrix. Every time I do this talk, I like to give a picture of mesizing. Unfortunately, I couldn't find the picture that I wanted to show in Sao Paulo, so I had to use this picture in New York instead. So this is the Empire State Building, but this is not what I'm interested in. I'm interested in this shop down here. This is Build-A-Bear Workshop. And if you've ever had a kid, or you've ever taken a kid into the shop, you will know what you do. You go in, and you basically, as the name suggests, build a teddy bear. You pick the outside of the teddy bear, you pick the stuff in, and you sew it all up. And this is really what we do with guts. We build the gut in the same way that a kid would build a bear in this shop. So let me use this as an analogy. The first thing you do when you build a bear is you want to pick the outside of it. You want to pick the thing that you show off to your friends. You want to pick basically the foundation of it. And this is the same thing we would need to do with the gut. We want to pick the gauge loop. There are 340 different possibilities, so let's just choose one. I've given 4 here. And I've given them 4 here because they have the smallest fermionic representations. So out of that list of 340, these are the only ones with 2 or fewer fermionic representations. And what me and Joe DeFigi, the person I did this half of the project with, did is we basically went through this list, and we said, can we make a gut that works? So we started with SO10 plus SU3, plus SU2. And we asked, is this going to be an interesting model to base our project on? And we decided probably not, because this is just SO10 with an SO3 flavor symmetry. So there's probably not much useful, or not much interesting things that can be said there. We then went down to this one. So this is color flavor unification, so you're kind of combining flavor with the SU4 part of Pâté Salame. And we asked, can you construct fermionic masses and mixes with this? And we went through the whole process of constructing our bear or constructing our gut. We put all the fillers in, we tried to sew it up. And then we looked at our final product and we were like, yeah, we don't really want to show this to the world. So we ended up throwing it away. And it's in a bin somewhere, and probably never to be revived. But we couldn't get things to work in quite the right way, or quite the nicest way we would want. So we went back to the drawing board, and we went back to this list, and we went one step further down. We went to SU4 plus SP6 left plus SP6 right. And we were like, can we construct a gut, a model, a theory of fermionic masses based on this? And the answer to that, given my second half of the talk is about this gut, is obviously yes. I should say that if we had went down to this model, we suspect things would have also worked in a very similar way to this. So this is kind of like color flavor unification, except you're combining with the U1 right or Pâté Salame rather than the SU2 right, Pâté Salame. Okay, so before I proceed, I need to tell you what SPN is. I know we had SPN in the talk yesterday and a couple of talks last week, but this is just in case you couldn't that's a typo, that should be SP6. This is the definition of the SP6 gauge group and the SP6 gauge alpha. And this, you don't really need to remember this, I just want to show you a definition exists, and this is it. So SP6 is really defined as a subgroup of SU6 which satisfies this condition, which is really saying it has an antisymmetric bilinear form, which is contrary to the definition of SO6, which is that it has a symmetric bilinear form. This definition only exists for even n. There's no such thing as SP5 or SP7. There's only things like SP4, SP8, etc. Okay, so this is really just to show you that a definition exists, and this is the definition that we're going to use. There are non-equivalent definitions, but this is the one that we want to focus on. So we have the outside about there. We have the outside. We have really what if you told me what this model is about, I would tell you it's SU4 plus SP6 plus SP6. What we now need to do now is we need to give it the fill-in. We already have some of the fill-in. We have the fermionic content. So that was given to us for free in the last half of the talk. What we need to do is we need to put the rest of the fill-in in, which is the scalar content. And when you do this, you might need two different types of scalars. You need the scalars that do the symmetry breaking, and you need the scalars that you need to do the other thing you're trying to do with your model. It turns out for our model, you only need the format. We're going to try and do fermionic masses in the CKM matrix and try and predict those. And it turns out that the only scalars we need are those related to the symmetry breaking pattern. So let me show you how we're going to break symmetry.
So before you go there, out of the 340 that you had, why did you pick this one?
So it's based on the fact it's just that it's got the fewest number of fermionic representations. It's really the nicest compact guide. It's the only one which, well, okay, the others have like different representations. They're like SU5 plus SO10 plus Patterson, things like that. So these are the ones where things are unified to the greatest extent, let's say, at least in the fermionic sector.
Do you mean the fewest fermionic representations, or which?
So
like the fewest fermionic representations?
Yeah, so where the fields combine into the fewest representations. Yeah, I mean, you could have chosen any of these 340. We had to choose one, so we based it on this criteria. There's a whole load of us in this list that could be studied. I know, for example, Patterson cubed, which also appears in our list, has become popular amongst the anomaly people. There's a bunch of other stuff. So all of these things that you kind of see in the literature are related to Patterson and by 3 copies of SO10 there on our list.
So get this color and SU2 here.
Oh, so color list in. I can show you actually the symmetry breaker. It's probably best. So yeah, so this is, I changed the gauge groups, I don't know why, but yeah, so this is our gauge algebra, SU4 plus SU6 left plus SU6 right. And really this is the same way that Patterson works. So the U1 sits in this SU4 and the SU6 right, and the standard model SU2 sits in this SU6 left, along with flavour symmetry on your left-handed course, and there's a flavour symmetry on your right-handed course sitting in there. So let me just focus on the left-handed for now. The first thing we're going to do is we're going to break the SU6 left with this field of S left. By the way, actually, you don't need to remember the details of any of this for the rest of the talk. This is, the rest of the talk, this is not so important. I just want to give you a flavour of what the scale content looks like. So yeah, we're going to break this SU6 left down to 3 copies of SU2. So we're kind of doing like flavour deconstruction of the SP6 into 3 copies of the SU2 left, one of which acts on each of the 3 families. We're then going to unify those 3 flavors that we've deunified with this linking field, phi left, which combines these 3 copies of SU2 left into 1 copy of the standard model. So this standard model SU2 left basically just sits in this SU6 left. For the right-hand sector, we do essentially the thing you would do for a Patis-Lamb model. We take the SU4 and the SB6 right, and we break that down using this field S right to an SU3, which is the color. So that SU3 sits entirely in the SU4, and then an SB6 right and a U1 right. This U1 sits part in there, part in the SU4, part in the SB6 right. This phi right field then takes these two things and breaks them down to hypercharge. And this is how you get to the standard model. And like any Patis-Lamb model, we need 2 Higgses to break this down. But you don't need 2 Higgses, you only need 1, but to get our things to work, you need 2 Higgses to break it down to break electroweak symmetry down. So this is the scalar content of our model. And this is all the scalars that we're going to need. The kind of the scalars that are kind of forced upon you by symmetry breaking. We've chosen the minimal dimensional representations, which would do the job of this symmetry breaking. So the other thing I'm going to be interested in is this epsilon here. I just want to signify that this epsilon is going to be some small number. It's not going to be that small, it's going to be order 0.2 in the end. But it signifies the difference between these two scales. The scales where we're going to integrate out heavy components of the Higgs and this symmetry breaking here. So this is really the fill-in of our model. And what we need to do now is we need to sew it up and get the final product. Something that we can show to our friends, something that we can put on the archive, something that we can publish. And what me and Joe decided to do, what me and Joe could have decided to do is any of these things. I mean, this is a gut, so you can pretty much do anything you want. But there's a big range of things we could have looked at. So we could have looked at fermionic masses. We could have looked at trying to get the PMNS matrix to work. We could have done low-scale unification. Can we bring the scale of unification really low? We could have studied things like the B anomalies. We could have looked at cosmic strings or monopoles. Of course, we didn't have the time or the energy to do all of these, so we just chose fermionic masses. But these kind of show the possibilities of what else needs to be done for this model and what else can be done with these sorts of
Why
parts.
do you want low-scale unification? Why not unification to start with?
Ah, yeah. Okay. Yeah.
So
Do the cosmic string.
this is already a stage where in principle you could check whether there is a topic unification.
Yeah. I think we conclude. I think we concluded something like that it would follow basically what Patis-Lamb does, but I can't quite remember. But yes, I agree. This is where we could look at.
But does it even have a meaning that when you have a product group?
Yeah, exactly.
So what would the unification mean here? I mean, you have 3 groups,
I have 3 groups of them.
3 continents, no? There's no condition.
So all the gains, well, there's some interrelation between the hypercharge that lives in Rho. I don't know that. It's probably enough 3 parameters to
Yeah, but so this needs to be, I mean, we haven't looked at anything like this. We were just trying to we focused on the fermionic masses as a first sort of approximation. Let's say. So,
by the way, have you checked for perturbativity? Because
for what's that?
for perturbativity of the one, I guess it doesn't matter if you don't want to.
Yeah, I think so. Yeah.
Because you had all these representations for the
Scales. Yeah. Yeah, I mean, okay, I can hold my hands up and say there's lots of things here that need looking at, that need studying. This is like, you could do a bunch of things with this stuff. We didn't do everything, just because we didn't have time, I guess. So, let me focus on fermionic masses. So to do the fermionic masses, we need the Yukawa terms. And I'm not going to show you explicitly how we get the Yukawa terms. I'm just going to show you this slide. Again, this is complicated and dense, so it's not that important you understand this, but I just want to give you a flavor of how we get these terms, how we get the Yukawa matrices in our model. And it's basically following a set of rules. So let's say we want to get the free-free component here, the free-free component of the Yukawa matrix. I'm going to focus on the down type Yukawas, the other types working like the same way. What we need is 3 blue arrows here and 3 red arrows here. This basically means it's the free-free component of the Yukawa matrix. So we're kind of making and inventing these rules, these color diagrams. And there are these rules up here about what the fefs take in and give out. And we need to go from three blue arrows to 3 red arrows. And you can see from these that the quickest way to do that is using 1 Higgs. So we can put Higgs there and we get this term here, which gives us the Y33 component. And you can do the same with the other components and play the same game. So for the 1, 3 component, you have 3 blue arrows here and 1 red arrow there. That corresponds to the 3 there and the 1 there. And you can use these rules up here, which correspond to the fifths, which I haven't given you. And I'm doing this all very hand-wavy. But you can use these to try and get from 3 blue arrows to 1 red arrow. And you can see that the quickest way of doing that is like this here. And these spies, they come with the epsilons. Remember I introduced this epsilon, which was the difference in 2 scales, the scale which we integrate out of the heavy Higgs, and the scale where the symmetry gradient that the phi lefts and the phi rights occur. So these are small numbers. So this 1, 3 term, using these up here, comes with 2 epsilons. And the 2, 2 component here comes with 2 epsilons of a different type. So you can construct the whole Yukawa matrix. If you don't understand that, don't worry. Just take it that you can use these sorts of diagrams to construct the Yukawa matrix. And the Yukawa matrix ends up having this sort of structure here. And this really completes the bear that me and Joe were trying to make. So we've been to the store, we had got the outside of the bear, we had chosen the gauge group, we put all the filling in, and we'd sewn it up to get something which is complete. We then take this, our toy, our bear, to the playground, and we need to compare it with the cool kids bear, in other words, the experimentalists. Because they have one where everyone has to compare it next to. And the experimentalist says, okay, you have this Yukawa matrix, but experiment shows, or my bear shows, that there's a hierarchy in the fermionic masses. And they say, can you get a hierarchy in the fermionic masses using this Yukawa term? And we're like, okay, we'll find the Yukawa, we'll find the masses of the fermions. So we do singular value decomposition of this matrix, and you find the fermionic masses. You get that the first family has 4 epsilons. You get the second family has 2 epsilons, and the third family has 1 epsilon. Sorry, that's no epsilons. So here we have a hierarchy, as long as these epsilons are small, in the fermionic masses. Then the experimentalist is like, okay, fine, you can get the hierarchy in the fermionic masses, but can you get the CKM matrix? Because the CKM matrix is slightly more difficult to achieve than this. This is pretty easy. So me and Joe were like, okay, we'll try and find the CKM matrix of this. So we do the necessary computations, and we end up with this thing here. We end up with this thing here. So C1, C2, C3, they're just constants. They depend on the scalar potential, which I haven't shown you when I haven't bothered to write down. And there are these epsilons, which I've already introduced. So you have this structure, and if you look at this, and you set epsilon left 2, 3 to be lambda squared, and you set epsilon left 1, 2 to be lambda, you get this structure here. So this corresponds to the same structure the experimentalists see. This corresponds to the Bibo angle, it's lambda. And so we kind of get the same hierarchical, or we can achieve the same hierarchical structure that the experimentalists see by setting these epsilons to be specific things. This is not quite good enough though, because experimentalists is there and they ask the question, okay, fine, you can get the hierarchy correct, you can get the hierarchy in the fermionic masses correct, but can you get the precise numbers? In other words, there are order 1 numbers I've left undetermined here and here and here. Is there enough freedom to fit the data? And there are 3 possible answers to this question. The first answer is no. We can get this, but we can't get, there's not enough freedom to actually fit the precise values of the data. If that was the case, I probably wouldn't be talking to you about this model. The second answer to that question is yes, there is enough freedom. But there's enough freedom that we could have fit any matrix you gave us, as long as it was unitary. That answer is perhaps boring because it just shows that your model has like far too much freedom and you can fit the data. You can fit the data with anything. The third possibility is perhaps the most interesting. The third possibility, or the third answer, possible answer to to this question is we can't fit every matrix. We can't fit every unitary matrix. We can only fit unitary matrices which satisfy certain conditions. And then and given that, then you can test whether the standard model matrix, satisfies those conditions or not. So it's kind of like a prediction of your model. It turns out that it's this latter case that our model fits into. In other words, if there were random order 1 numbers here, we could not fit this matrix. We can only fit this matrix if the order 1 number satisfies certain specific conditions. And these conditions happen to be these things. And they are kind of like a consequence of the Wolfstein parameterization. J here is the jar-slugging variant, then I'm using the fork notation, I guess, to write down the CKM matrix. So as long as the experimental data, or the main point is, as long as the experimental CKM matrix satisfies these conditions, then we can fit it. If they don't, then we can't fit it. And if you plug the experimental data into this result, you get that it fits into a fairly good approximation. So we're in this third situation. It's a situation where there is enough freedom. Sorry, there's not enough freedom to fit any possible matrix we want. There is enough freedom, however, to fit the standard model. Okay, so this kind of concludes the second half of my talk. Let me give you the 3 takeaway points. I've been looking at Electroweak, flavour, unification. I've been taking Patti Salam and I've been unifying the Electroweak part of Patti Salam with flavour. And we get, given our scale of content, a correct prediction of the CKM matrix and the masses. And there's also lots of exciting works, possible work, or possibilities for future work. That whole list of like neutrino masses, things we've been talking about, couplings, all of this stuff have been left undone, and we need to do them, and we're working on them, albeit slowly. So this concludes my talk. If you have any questions, or if you have any feedback on how I've given this talk and how you might think the talk can be done in a better way, let me know. Yeah, and that kind of concludes it.
Thank you, Joseph. So, more questions for Joseph? Please go.
Okay, can you go back one slide? No, one more, sorry. Yeah. So you said, for instance, this BTS BCD, this would be equal. That's not true in practice, no? It's like one, so the third problem, so it's the third relation. That is a,
This one.
yeah, that is what really two elements, and the other one is CD, which is a 2-1 element. So they are not even the same order, no? Or misunderstood?
Maybe it could be that, but typo here as well.
I mean, the only one that are really in the arrows maybe of the same order are the 2-1 and 1-2 elements, right? All the others are not equal in the experimental error.
So okay, I'm pretty sure these, or the least, there could be typos on the slide, but the conditions on the paper, in the paper, I'm pretty sure they all hold within one same
I
mode.
want to check, but I don't think there are so many. I don't know, I get, well,
Yeah.
maybe the diagonals, okay, the diagonals are all one, no, okay.
Yeah, I mean, okay, I
So
don't
I
know.
will look them.
Yeah, I don't know off the top of my head, sorry.
But even the first one, I guess, that's 1-1 and 2-2.
So this is the 1-1, and then the CS is the 2-2, yeah, that should also not be I think there are some.
No, this one works. Right? You plug that squared into that, you get that relation.
Oh, square.
Oh, it's a square.
Sorry, my bad.
Yeah. Yeah, I mean, okay, the only thing I can say is I'm pretty sure they were checked.
And also the second and third are the same.
Yeah, sorry. It would probably be easier if I numbered these with 1, 2, rather than these you down in the version.
Which one is easier to falsify? I would guess something with QB, but we currently have some issues with that.
Yeah, I mean I have these all follow really from the JAWS from the Woodstock parameterization. So they are fairly well known, except for this one. I've never seen this one, but it does follow from standard results. I think this was the biggest surprise that this one worked. Yeah, just takes account of like CP violation, etc.
So, did you take into account the running of the?
No, we haven't done anything like that. We were literally, can we do permanent analysis? Yeah, we're currently looking at the B anomalies, things like this, where perhaps it's probably become more important. Yeah, we haven't taken account of it or anything like that.
So I think I remember that when you run up to some get scale, the shape of the matrix changes.
Yeah.
It was more symmetric.
Yeah. Yeah. I should say we can have our gut can really live. We don't have proton decay, so we don't have that constraint to worry about. The same way the Python doesn't have proton decay.
Why do you know? Because there's no X-like input.
Yeah,
because it's
yeah.
not an actual unified.
It's exactly right. Yeah, it's the same for like exactly the same reason Python doesn't have it.
Do you actually have one concrete prediction for the fermion masses, or it's still a class of that wasn't completely clear?
You mean of what they're going to be?
I mean, the fermion masses. Do you have actually,
Like numbers?
I mean, probably there's something for you that.
Yeah, I mean, so these order one numbers, they depend on the parameters of the scalar potential, right? And what this is saying is, as long as these conditions are satisfied, then there is enough freedom in the parameters of the scalar potential to actually hit the numbers bang on, if that makes sense. So it's not like we can predict. It's not like we can, given the CKM matrix, predict the fermion masses. We can't do that. The only thing we can say is that if experiments deviate from these results, then we have to worry.
When you listed the parameter for the guts, so you split them up in 1, 2, 3 families, right? So is that just the number of families of the gut fermions?
Yeah, sorry, I shouldn't. So the one family was just take one family of the standard model, take the 16, like just take one left-handed Borg, one right-handed uptype Borg, etc. Just take that, find the guts of that. And then, so you can actually get all of, you only have to do the calculation once, you can get all of those results from the free family case just by like quotients and out, that sort of things.
Okay, very good then. So I think it's lunchtime, so let's thank Joseph again. Let me just remind you that tomorrow